Hello everyone. In this video, we are going to discuss data representation in computers. In the previous video on computer memory, we did mention to say digital computers represent data in digital computers is represented using binary numbers. That is binary digits, either a 0 or a 1. You could have your data could be in form of a picture, or it could be a video, or any other media, text, for example. When it comes to representing the data inside the computer, this data will be represented as a series of zeros and ones. So in this video, we want to look at um, data representation in computers. So I've already mentioned to say, when we talk about the input, when the computer is processing the data, what we've said, what the computer does is it accepts data, process the data to give the desired output. That's from the definition of the computer. Now, this data which we enter could be in form of letters from the alphabet. It could be digits, it could be symbols, it could be audio or video, etc. Now, um, when this data is entered, digital computers can only understand zeros and ones. So whatever data that is entered, it has to be converted into these digits so that the computer can understand the instruction that you are giving, the data that you are giving, and so that it can even process this data. So in this video, we'll look at the concept of the number system. We'll look at the concept of a number system because this is important if we're going to understand how a computer works. Now, what we are going to discuss is something which most of you are already familiar with. You've talked about decimal number systems. You've talked about octal number systems, numbers represented in base 8, binary number system, numbers represented in base 2. So those are the things which we want to discuss in this video. Okay, now when we talk about a number system is a writing system for expressing numbers. When you want to express a number, you use a number system. Now, what this number system does is the number system defines the characters or the digits that are acceptable um, for expressing numbers. So, for example, if we said, for example, one of the most common number system is the decimal number system, the one which we say base 10. Now, in the decimal number system, basically the digits that you use to come up with numbers will be digits from 0 to 9. So these are the digits that you use to express numbers in base 10. Okay, now if we talked about the binary number system, the one which we express to say in base 2, again, the digits that you can use to represent your numbers are just those two. So when you're expressing a number, depending on the number system that you use, there will be a set of digits that you can use. This concept is similar to languages. If, let's say, I'm communicating a message in English, for example, there will be a set of words that I can use. And if I try to use any other word outside that set of numbers, that set of words, it will not be accepted in the English language. If we looked at local languages, let's say, for example, Bemba, you find that we have a set of words in Bemba which we can use to express a message. Now here we are talking about numbers, expressing numbers in uh, expressing numbers. Now, when it comes to expressing numbers, we have the concept of the number system. And for this concept of number system, we are saying it is a star or a writing system for expressing numbers. I hope that makes sense. Now, every number system will have a base. Now, the base will guide us to say these numbers are represented, for example, in a binary form, or they are being expressed in octal, they are being expressed in decimal. Okay. Now, every number system, so a number system in base R will use unique symbols for R digits. What we are trying to say is this. When we talk about binary numbers, when we talk about numbers in base 2, okay, so for numbers in base 2, you are going to express them using these 2 digits, 0, 1, and 0. And then to even indicate the number system that you use, you're going to put the base at the bottom here as a subscript. So what this means is that this number is being expressed in base 2. Now, what this statement is telling us is for a number system in base R, and R could be any number, it means we're going to use that number of unique characters. Numbers in base 2, okay, binary numbers. Whatever number you want to express, you will express it using the 2 digits, 1 and 0. If we talk about decimal number system, we have 10 unique characters, the unique digits from 0 up to 9. So whatever number that you want to express will be expressed like that. So when we are coming up with a number, we are going to get one or more digits and we'll combine them to get our number. So that is about the number system. Okay, so the number system will determine which digits are valid and which digits are not valid. So for example, again, if we use let's say the binary as an example. So for the binary system, the digits that are accepted are these. So if someone was to write to say 431 and then they put the base, let's say for example they put the base 2 here, this is not valid. Why is it not valid? Because in the binary number system, the only digits that are accepted are these 2. So anything outside this set of numbers that we have will not be accepted. So that's what this point is trying to say. Now, in the number, when we're trying to look at the value of that number, we consider the positions. Okay, we consider the positions, and the position will start from the right going to the left. So the rightmost digit has a position 0. The next number, the next digit on its left has a position 1. The next one, position 2, just like that. Don't worry about this, it will make sense. So let's say, for example, let's say 1101, and let's suppose this is in base 10. Now, what this means is this position, the rightmost position in this number, has a position of 0. So it has a position. This position is position 0. Then the next position is position 1. Then this position is position 2. And this position is position 3. So it's important to understand this concept of the positioning of a digit in a number. So the rightmost position will have the position 0. So this last position is position 0. The next position is position 1. The next position is position 2. The next position is position 3, just like that. Okay, so that is about the positioning of numbers. All right, so now let's move on. Now, when we talk about number systems, the digits in a number, the digits that are making up a number have two kinds of values. The two kinds of values that we have what is called the face value, and we have what is called the position value. So there's a face value and there's a position value. Now, the face value of a digit, when we talk about the face value of a digit, we are saying what number can we see, what digit can we see located in that particular position? What digit can we see located at that particular position? For example, in a number like this one, where we have 52, the face value in this position, position 0, is 2. The digit which is in that particular position, the digit which is in that particular position. In position 1, the first value that we have is 5. The first value, the digit which we can see in that position is 5. Okay, so now we've talked about the concept of the first value. So now let's look at the concept of the position value. Now, the concept of the position value, we are looking at the actual weight of that digit in that particular position. So the position value of a digit is the base raised to that position. Okay, so basically what we are trying to say is this: when you have a number like this one, the first value of this digit in position 0 is a 2. The first value of 5 of the number in position 1 is a 5. Now we want to see the actual width. Now, when you were doing your primary mathematics, arithmetic in primary school, you did learn the concept of, for example, when you're dealing with base 10, okay, let me just write this. So you said we have ones, we have tens, you have hundreds, you have thousands, you have 10,000s, etc. Now, if we have a number like this one, let's say 125. Okay, when we talk about the first value, the number that we can see on the face of it, this position has a higher digit. But then when we look at its position value, these are 5 ones. Then these are 2 tens, which is 20. This is 100. So that is the position value, and that's what we are trying to communicate here. So when you want to get the position value of a digit, the way we calculate is like this, where we say the first value in that particular position multiplied by the base raised to the power. So for example, in a number like this one, the position value for 2 is going to be 2 multiplied by the base, which is 10, and then what is that position is 0. So 10 raised to the power 0 is 1. 1 multiplied by 2 will give us a 2. And then the value for this one, the position value for the 5 will be 5, which is the first value, multiplied by the base, which is 10, raised to what's that position? This is position 1. So 10 raised to the power 1, that is 10. 10 multiplied by 5 will give us 50. Okay, so this is the position value, and yeah, this is the position value for a 5, and that's the position value for the 2. So that is the idea. All right, so this is how we work out the position value of a particular digit. So in any number system, it's important to understand that concept of the first value, and also the concept of the first value and the position value. So now let's move on. In computing, the number systems of interest that we look at, the decimal number system, the binary number system, the octal number system, and the hexadecimal number system. So the hexadecimal number system, that is the base 16. Then octal number system, we're talking about numbers in base 8, and then binary numbers in base 2. Now, when we are expressing a number in a particular number system, the base is indicated at the bottom. So here, for example, if we have a number like this one, 23, and the 10 at the bottom here, this is indicating the base. So we are saying this number is expressed in base 10. It's expressed in base 10, and yeah. Okay, then if we have a number like this one, 3, 4, 5, 8, so this number is expressed in base 8. This shouldn't confuse us, because we are already used to this concept of expressing values in a particular unit. Let's talk, for example, mass, how heavy something is. If we want, we can express something in kgs. If we want, we can express something in grams. So let's say, for example, for a packet of sugar, I can say this packet of sugar is 1 kg. Okay, and I can express the same mass to say this packet of sugar is 1000 grams. So the gram, the kilogram is expressing the system that I'm using to express that. That is a similar thing which we are doing here with number systems. We are saying this number is expressed in base 10. This number is expressed in base 8. The most common base that we use on our daily basis is this one, the decimal number system, in base 10. All right. Okay, now let's start with this decimal number system. With a decimal number system, remember what we said was that for any number system, the number system itself defines the digits that are accepted in that particular number system. So for example, in base 10, what we have is in base 10, what we have is we have 10 digits that are used to express numbers. So all the numbers that you're going to write in base 10, they are going to be a combination of digits from 0 to 9. So you can have a number like this one, 34, you can have a number like this one, you can have a number like this one. So all the digits that you are going to express will be in this using these digits. That's the decimal number system. Okay. Now, just to say something about the concept of positions. Remember when we are calculating the first value, we did say when you have numbers like this one, the rightmost number, the value in the rightmost digit, in the rightmost position. So this is position 0. Then as we are coming to the left, position 1, position 2, position 3. Now what I need to make mention of also is in some numbers, we do have decimal values. They do have, we do have a decimal point and numbers after the decimal point. Now, for these numbers after the decimal point, they are positions. So from the decimal point coming to the left, coming this side, we have position 0, position 1, position 2, position 3. From the decimal point going to the right, from the decimal point going to the right, what we have is as we go this side, the positions are negative. So this is position -1, position -2, position -3. Okay, so that's something which I needed to mention. All right, so that's about the decimal number system. The octal number system. In the octal number system, when we are expressing numbers, we are going to express them using 8 digits. The 8 digits will be from 0 up to 7. 0, 1, 2, 3, 4, 5, 6, 7. In octal number system, you cannot use digits 8, digits 9. They are not accepted in octal number system. So then the idea is in any number system, let's say for example the octal number system base 8. So the digits which you are going to use will be all the digits, the positive digits from 0 up to 7, for example. That's for base 8. If it's base 2, which we'll talk about shortly, you can only use 0 and 1. You cannot use a number equal, a digit equal to or more than the base. So base 8, meaning you cannot use 8, you cannot use 9. Base 2, you cannot use 2, you cannot use 3, you cannot use 4, you cannot use 5, you cannot use 6, 7, 8, 9, you cannot use any of those. So that is the idea. So again, in terms of the concept of position, it's just the same thing. And calculating the position value, we calculate it the same. Remember what we said about the position value? We said to calculate the position value, you are going to look at the first value, the value in that particular position, multiplied by the base raised to the power position. So this is what we said you do. So even in base 8, that is how we calculate. In base 10, when we want to know the position value for any particular digit. All right. Hexadecimal number system. Hexadecimal number system. This number system, hexadecimal means 16. Okay. So in the hexadecimal number system, we have 16 digits from 0 to 9 and A, B, C, D, E, F. Okay. So remember we said any number system will define how many digits you can use. So in this case, we are going to use 16 digits. Now, in our way of counting using decimal, the highest digit that we have is 9. But here, we are saying we're going to have 16. So what we'll do, For a 10, to represent a 10, we use letters from A to F, where the letter A represents a 10, the letter B represents the 11, the letter C represents 12, D 13, E 14, and F 15. Okay, so that is what we use to represent numbers, digits, 10 to 15. Now, why can't we just represent them like this? For example, instead of putting a B in the number, or instead of putting, let me get this one, instead of putting F here and A here, why can't I just, why can't I have, we have 3, then F is 15, then A is 10. Now, why can't we have numbers in this way? The challenge that will be there will be, it will be difficult to tell that these two should be treated as one. Because there's a chance that if I wasn't there when the number was being written, I'll think this is position 0, position 1, position 2, so this is position 0, position 1, position 2, position 3, position 4. And the actual digit, the actual value which I had will be different if I was to convert or to represent like this. So to show that this one, these two digits are actually one, represented as one, that's why we will use a letter for that. Then even this one, to show that this one is 1, it should be treated as 1, we also represent it like that. We use F in place of 15. So for hexadecimal number system, this is how we express these numbers. The concept of position values, you are already aware. Now, how do we convert? Given numbers in a particular number system, it is possible to convert from one number system to the other. So for example, we can have numbers from decimal, we can convert them to octal, we can convert them to binary, we can convert them to hexadecimal. Okay, now when we're dealing with numbers, numbers will have two parts. The two parts that we have will be the fractional part and the integer part. So for example, in a number like this one, 23.078, the first part here will be the integer part, and then the other part here will be the fraction part. When we want to convert from decimal to another number system, we are going, the conversion, the way we are going to convert, the integer part will be converted differently from the fraction part of the fractional part of the number. So that's important to take note of. Okay, so let's say, for example, when you want to convert numbers from binary, from decimal to binary, what do we do? In converting an integer number from binary to decimal to binary, we use division. When you are converting integers from decimal integers, numbers in whole numbers in base 10, when you are converting them to another base or to another number system, we use division. So for example, when we want to divide, or when we want to convert 25 to 25 in base 10 to base 2, the things that we do are 1. You are going to come up with a table like this one. And in this table, you include 3 things. 1, you include the base to which you want to convert, the number that you want to convert, and the remainder. Now the remainder here, what we'll do is when I divide this number 2 into 25, I'm going to end up with 2 values. There will be the whole number part, the quotient, and there will be the remainder. So I need to record those two. Now I'll be recording them separately. The quotient, I'll be recording it here. Then the remainder, I'll be recording it here. So that is the idea. So each time we convert a number like this one, the quotient will be here and the remainder will be here. So you come up with a table like this one, where here you are indicating the base to which you want to convert the decimal number. Then in the middle, the number itself, and then the remainder. That is the first step. Then secondly, you are going to divide the number. And when you divide the number, you write the remainder on the right hand side, and then the result, the quotient, you write in the middle. And we'll continue dividing the quotient, taking note of the remainder until the quotient becomes 0. What I'm trying to say here is this. I want to convert 25 to base 10, to base 2. So I'm going to say 25, 2 into 25. Now 2 into 25 will be 2 into 25 will be 12, remainder 1. Okay. Next, I'm going to divide this 12. I'll say 2 into 12. 12 divided by 2. It is 6. There is no remainder. So I put 0 on this side. Then I say 2 into 6. It is 3. And what's the remainder? There is no remainder. Then I'll say 2 into 3. Okay, sorry about that. Let me just clean it up. Okay, so 2 into 3, it is 1, remainder 1. Then 2 into 1, it goes in 0 times, and then the remainder is 1. Okay. All right, sorry about that. Again, let me just clean up. All right. So this is what we said. So you keep dividing into this. Now, after you've done the division, the next part that you have to do is to read the numbers. Now, when you are converting integers from base 10 into base 2, what you do is you divide the numbers we have done. Now, when you're finished, you're going to read the numbers from the bottom going up. So 25 in base 10 is equal to, you start from here, you have 1, 1. I'm reading the numbers from the bottom going up like this. And then it's important to indicate the base, because if you don't indicate the base, the assumption will be your number is in base 10. So, and this is something that I think I need to emphasize. In any number system, it's important to indicate the base, because it will tell you, or it will help you to determine the value of that number. If you don't include the base, if the base is missing, the assumption is that number is expressed in base 10. So it's important to indicate the base of your number. Okay, so I hope that is clear. So this is what we do, and we said to read the number, you convert, or you read the numbers from the bottom going up. In your own spare time, you can try to convert these numbers. Now, we've talked about converting numbers from base 10 to any other base. So when you have numbers in base 10 in decimal, and you want to convert to binary, to octal, to hexadecimal, what you're going to do, you're going to divide that decimal number by the base to which you want to convert. So for example, let me pick another one. Let's say, for example, 64 or 68. If I want to convert 64 Now these numbers are in decimal. So I'm going to come up with a table. So here I will have the base to which I want to take my number. So this is I will indicate the base to which I want to convert. Then here there will be the number itself, and here there will be the remainder. So if I want to convert a number to base 16, so let's say, for example, I think let me do the third one. It looks interesting. Okay. All right. So I'll say 16 into 29 is 1. Using the division, the concept of division. Now, 16 into 16 into this, into 29 is 1. Is 1. And then the remainder that we have is 13. Then I'll continue. I'll say 16 into, don't mind the way up. Okay, let me write it nicely. All right. 16 into 1 is 0. The remainder 1. And then I have to read the number from bottom going up. So I'll get this 16, the first digit here, 1. Now, this 13 it should be treated as a single number. So 13, I think, is represented by D. 10 is represented by A, 11 by B, 12 by C, 13 by D. So if I convert to base 10, this will be 1D in the base 16. Okay, so I decided to do this so that I can show you how to deal with numbers like this one. You shouldn't, when we convert like this, you can't write it to say 113 in base 16, because the way it will happen, or the way it will be considered, will be this is in position 0, this is in position 1, and this is in position 2. But what we have, each value that you have here is supposed to occupy one position. As we convert here, this one will be in one position. This one will be in one position. So that's why I took this to I represented it with using the character which it has been given. So if you wanted to convert these numbers in base 8, you can follow the similar procedure like we have done for base 2 and base 16. So hopefully this is clear. Now, the next part that we'll come to will be converting decimal fractions to other bases. Converting decimal fractions to other bases. So now the fraction part of a number. Remember we had that number 23.078. We have talked about how do we convert this integer part. So we've got also to look at how do we convert the fraction part of a number. To convert the fraction part of a number, what you're going to do, you are going to multiply. You multiply that number, the fraction number, by the base to which you want to convert. When you are trying to convert a decimal fraction to binary, you keep multiplying by 2. When you want to convert a decimal fraction to octal, you multiply by 8. When you want to convert a decimal fraction to hexadecimal, you multiply by 16. All right. So these are the steps that you take to convert a number from from base 10 to base to any other base. Okay, so the steps that you take are: 1, you multiply the fractional part, the fractional number, with to the base to get the resulting number. Now the resulting number will have 2 parts. You have the non-fractional part and you have the fractional part. You record the fraction, the non-fractional part of the number, and then you multiply the fractional part of the number. So you repeat this step at least 4 or 5 times, and then you write the digits in the non-fractional part, starting from from the top going down. Don't worry, let's do an example so that this can make sense. Let's suppose you have a number like this one to convert. 0.2345 from base 10 to base 2. The steps that you take as follows. You get your fraction, which is in base 10, multiply it by your base. Now, when you multiply your base, okay, which is, you want to convert to base 2, so you'll be multiplying by 2. 2 multiplied by 5, that's 10. So you write 0, you carry 1. 2 multiplied by 4, that's 8 plus 1, 9. 2 multiplied by 3, that is 6. 2 multiplied by 4, that is 4. Okay? Then 2 by 0, that's 0. So here, that is the first step. You multiply. Now, after you multiply, take note of the non-fractional part, this integer part. That's the one which you need to take note of. And then you continue multiplying the fraction. You continue multiplying the fractional part by the base. So again, in the next step, I'll get this result and then multiply it again. So I'll say this multiplied by this, it gives me 0.9380. Again, I'll take note of this non-fractional part. Then I get this other part, the 0.9380. Again, I'll multiply by 2. So when I multiply this, by this, it gives me 1.8760. I'll take note of this one, and then the fractional part, I'll multiply. When I multiply the fractional part, it gives me this. Okay. I take note of the fractional part, again I multiply. When I multiply, it gives me this. So I take note of this one and I continue. So I multiply like this, then it gives me this. So we said repeat this at least 5 times, 5 times. Now, why have we said at least 5 times? Because the multiplication can go on and on and on. When you are converting fractions from base 10 to any other base, you do estimation. You just estimate. You just do an estimation. You coming up with the exact value may not always be possible. But if you repeat the multiplication maybe 4 or 5 times, personally I'll prefer maybe let's say 5 times, the number will be quite close to the actual value in base 10. So that's about the multiplying. Now, after you've done the multiplication, you are now going to record those numbers you are taking note of from the top going down. So the first number that you recorded was 0. The second number that we recorded was another 0. The third number that we recorded is a 1. Okay, I'll put it all right. So that's a 1. Then this one. Okay. Then this one. So I'm reading the numbers from the top going downwards like that. So I've recorded this, and because we are dealing with fractions, I'll put the fraction here. So this is how we convert from base 10 to base 2. So this is a fraction expressed in base 2. Okay, so this is how we express fractions, or we convert fractions from base 10 to any other base. So if you are trying to convert to base 8, you multiply by 8. If you are trying to convert this fraction to base 16, you multiply by 16, just like that. So that is the idea. Okay, so let's now continue. All right, so this I've already explained. This you can try. Now, when we are converting, so let's say I have a number 23.79, for example. When it comes to conversion, you convert the integer part the way we did, and then you also convert the decimal part, so the integer part you convert, and even the fractional part you convert, and then you can put them together. So for example, let's say if we try to convert this one, you convert 34 using the division, you record it. Then this one you also convert using multiplication, and then the number that you get, the first number, point the second number. That's how we'll do it. Now, converting from binary, octal, hexadecimal to base 10. When you are trying to take numbers from, let's say you have a number in binary, you want to convert to hexadecimal. When you have a number in hexadecimal, you want to take to decimal. How do we do it? The way we do it is you get the position value for those numbers. You get the position value for those numbers. Okay, so basically when you are converting, let's say you are in, the number is in binary, maybe just to picture what I'm trying to say. Let's suppose you have a number like this one. Let's say 1101 in base 2. And you want to convert this number to in base 10. So I've put a question mark. We don't know what that number will be. Now, when you want to convert from base 2 into base 10, what do? You get the position value for each of these digits. You get the position value for each of these digits, and then you add them together. So here we are saying find the sum of the position value for each digit in the number, and then you add them. So this is, for example, position 0. This is position 1. This is position 2. This is position 3. Now, to get the position value, this is what you do. You get the first value multiplied by the base, the current base, raised to the position. So, for example, let's say this one, this is in, what is its first value? Then the digit that we can see is 1. Then what is its base? The base is 2. Then what is its position? 0. So 2 to the power 0, 1. 1 multiplied by 1, it will give us 1. So we've gotten the position value for this number. Then we come here. This is 0. That's the first value multiplied by the base, which is 2, position 1. 2 to the power 1, that's 2. 2 multiplied by 0 is 0. Then we move on. We come here. Next will be, what is its first value? The first value is 1 multiplied by, what is the base? 2. What is the power? 2. So 2 squared, that's 4. 4 multiplied by 1, that is 4. Okay. Then we have the last one here, which is the first value is 2, is 1. Then what is the position? The base 2. What is the position? 3. 2 to the power 3 is 8. 8 multiplied by 1 is 8. So now, here we are told to say, find the sum of the first value, or find the sum of the position value. So this will be 8 plus 4, 12 plus 0, 12 plus 1. So this will be 13. Okay, so when we are converting 1101 in 1101 in base 2 to base 10, this is what you end up with. So this is how you do it. If you are dealing with base 16, if this number was in base 16, all that will change is the base here. Basically, it's the same procedure. Okay. Let's see if we have another example that we can use just to strengthen our understanding. When you're dealing with fractions, remember we said in a number, let's say, okay, let me write it down. Let's say you have a number like, we're just interested in the fraction part. So we have 0.1101 in base 2. Again, when you are converting, the procedure will just be the same. You find the position value and then you add them up. Now, the positions, this is position -1. Positions after the decimal point are negative. So this is position -1, position -2, position -3, position -4. This is how we do it. So this number here, remember the concept, to get the position value, you get first value multiplied by the base raised to the power. So we get this one. This will be, remember the formula, the first value, let me just write it as FV, multiplied by the base raised to the position. Raised to the position. Okay, so this will be, what is this first value? 1 multiplied by the base 2. Then what is its position? The position is -1. Now, 2 raised to the power, so this will be 1. Now, anything that has a negative power is the same as 1 over that number raised by the power. So this is the same as that 1 over 2 to the power 1, which will be 0.5. 1 divided by 2 is 0.5. So when you calculate this, you end up with 0.5. Then let's come here. This is position 2, position -2. So this is the same as 1, which is the first value here, multiplied by the base, which is 2, and then the power -2. Now, this 2, or let's say this, let's say anything, okay, let me clear this. All right, so generally, when you have a number raised to the power -a, this is the same as 1 over 2 to the power a. So the negative is indicating to say this will be a fraction. So it will be 1 over 2 to the power, that particular power. So this will be 1 multiplied by 2 to the power, okay, so this would be 1 over 2 to the power 2, which will be 2 squared, that would be 1 over 4. When you perform this calculation, you end up with 0.25. Okay. Then next, this is position -3, which has a 0. Then position -4 will be, for this one, the calculation will be 1 multiplied by 2 to the -4, which will be 1 divided by 16. You get your answer. Okay. Okay, so when you perform this calculation, you end up with 0.0625. So what you now do is you add these numbers. This plus this will be 0.75, 0.75 plus this number. And then you will have gotten your number in base 10. So that you can work out. So basically the same concept. Get the position value for each digit, and then when you get them, add them together. That will give you the result. All right. Okay. So that's how we convert from decimal to binary, and then from any other base back to decimal. This is how we will do it. All right. So basically, these are the same things I was trying to say. So these examples, you can try them on your own. So let's say for a number like this one, 0.15, which is in base 10 to base, which is in base 16, converting it to base 10. This is how we do it. And the answer will be this 0.15 in base 16 is the same as 0.82 in base 10. All right. So these are just examples which you can work on. Now, there are situations where we want to convert a number in base 16 in binary. Okay. Okay. Yeah. There are situations where I have a number which is in binary and I want to convert to octal. Now, there are two possible options. The first option is I can get a number which is in base 2, convert to base 10, and then convert the number from base 10 to base 8. Now, that will be a lot of work. There's a shorter route. Now, the shorter route is when we are dealing with an octal number. When we're dealing with an octal number, the highest digit that we can have is 7. Okay. Now, this number, when we express it in base 8, it's going to use 3 bits. Okay, it's going to use 3 bits. So what we do when we have a number in base 2 and we want to convert to base 8, what we do is we are going to group the number in 3 bits. So what I'm trying to say here is this. When you have a number, for example, okay, let me write it here. 110 1 0 0 0 1 1 1 1 0 1, and this number is in base 2. Now, when you want to convert this number into base 8, you want to take this number to base 8. What do we do? What we do is we are going to, from this number we have, we are going to create groups of 3 bits. Okay. Now, bits, remember, it's just binary digits. So every 3 binary digits, one group. Every 3 binary digits, one group. Every 3 binary digit, one group. That's what we're going to do. Now, this will be done from left, from right, going to left. So let me just change the color so that we see what I'm going to do next. All right. So the first 3 bits from left to the right, from right to the left, sorry, I group them. So this will be one group. Then 1, 1, 1. So again, these are 3 bits. I'm trying to convert to base 8. Please take note of that. Then this is 3. Then, so 1, 2, 3, I group them. Then again, 1, 2, 3, I group them. So this will be another group. Then the next one, 1, 2, 3, this will be another group. Then whatever remains will also form a group. If I want, I can put zeros, or it's still fine. This is another group. Now, for each of these groups, this represents a number in base 2. So get their first value. I'll get their position value. So if you have a number like this one, 101 in base 2. Remember how we are just from calculating the position value of a number. Get the position value of 101. It's similar to, it's like you're converting to base 10. So when you convert this number from base 2, so this will be position 0, position 1, position 2. So this number, if you convert this number using the conversion we are just from talking about, it will give you a 5. How? So this will be, for the first one here, it will be 1 multiplied by 2 to the power 0. This is position 1, but we know that anything multiplied by 0 will be 0. So to speed up, or anyway, so that we are not confused, I have this one multiplied by 2 to the power 1. Then I have this, the third one, which is 1 multiplied by 2 to the power 2. 2 to the power 2. So this would be 1 multiplied by 1 is 1. 0 multiplied by 2, 0. 1 multiplied by 2 squared, that's 4. So 1 plus 4 gives 5. Then, so this will be a 5. When you convert 111 in base 2 to base to use, you get the position value, it will give you 7. Okay, then this number, it will give you 0. So all that I'm doing is this converting, getting their first value, similar to what I did here. Then this one, it's a 5. Then this one will be a 1. So it will be 15075 in base 8. So I hope you have seen what I've done. When you are converting a number from binary directly to base 8, what you do is first you group them. First you group them like this, and after you group them, for each group of 3 bits, when you're converting to base 8 to octal number system, you create groups of 3. It's very important to take note of that. All right. So we've done that. Then even here, we've converted like this. I've converted the number from base 2 to base 8. I hope that makes sense. So these are the steps we're talking about. Partition the binary number in groups of 3 bits, starting from the rightmost, going to the left. The result that you get for each group, you will now find its octal number, which will give you a number in base 8. So that is the idea. So this is another example which you can go through. First, you create groups of 3. This is what has happened. After creating groups of 3s, each of these get their position value. After getting their position value, it will give you the number in base 8. So that is the idea. Now, when you want to convert a number in binary to hexadecimal, hexadecimal uses 4 bits. The highest number that you can have in hexadecimal is 15. Now, 15 in binary is 1111 in base 2. So this is 4 bits. So what you do when you are trying to convert a number from binary directly to hexadecimal, you are going to group that number in 4 bits. And then for each 4 bits, you now convert to, you now get the hexadecimal number. So the steps are 1, partition the numbers in groups of 4. After partitioning the numbers in groups of 4, you find the hexadecimal number of those 4 bits. The hexadecimal number of those four bits. Okay, and by so doing, you have converted the number in base 4. So let's look at an example. These are just numbers which I'm randomly thinking of. Okay. Okay, all right. I think here, so let's say this is in base 2 and you want to take to base 16. The first thing that you do, according to this number, you group them in 4. So starting from the rightmost again. So this will be the first group. After the first group, then next you have another group of 4. So which is there. Then next you have another group. Let me pick a different color. 1, 2, 3, 4. From here up to there. All right. Then the last one also will be a group on its own. So for each of this group now that you have, get their position value. So this one, if you get its position value, it will be 5. The concept of getting position values, you should now be confident in doing. So all that I've done is I have a number like this one. Then I say, let me get its position value. That's the one which has given me this. Then the next one, you have 0, 1, 1, 1 in base 2. Get its position value, which will be 7. Then for this one, this is interesting. 1, 1, 0, 0. When you get its position value, what it will give you will be, when you get its position value, it will give you a 12. Now, to represent a 12 in hexadecimal, we represent it by C. If you go back to the previous slides, when we were talking about hexadecimal, we said 10 is represented by an A, 11 by a B, 12 by a C. So here, where there's a 12, I'll put a C. And then this will be a 6. So 2, okay, yeah, this will be a 6. So this number in hexadecimal will be 6C7516. So this is how you convert numbers from base 2 directly to hexadecimal. I hope it's clear. All right. So this is the same example, another example. So you start by partitioning them in groups of 4. After partitioning them, for each group, get its position value, and then you'll be able to get your number in base 16. Now, okay, the next part that we'll look at is you have a number in base 8. You want to get to take it into binary. So what we've done, or what we are going to do in this case, we are going to do the reverse of what we are doing when we are converting numbers from binary to octal. Remember, from binary to octal, we started by grouping them in 3s and getting the position of the position value of each. Now, this time, when you have a number in octal, the steps that we take are as follows. For each number, for each digit in octal, you convert it into a 3-digit binary number. Please take note of this. You convert into a 3-digit binary number. So if you have a number like this one, 1763 in base okay, sorry, just a minute, let me write. Okay, so you have a number 1763 in base 8. and you want to convert this number to binary. Each of these numbers, each of these digits you see here, convert them into a three-digit binary number. When you convert 3 to binary, since it's a whole number, you use division. So this will give you 1, 1. But this time we're saying put them in as a 3-digit binary number. So to complete this number, since this just has 2, you put a 0 here. Okay? This 0 is just a placeholder. It says there should have been a number, but there's nothing here. So to complete the 3 numbers, because when you convert, if you just converted this strictly, it will just be 1, 1. But the rule is convert each number, each octal number, into a 3-digit binary number. So that's what we've done. Then when you convert 6 to binary, what you have will be 1, 1, 0. Then when you convert 7, the way that you convert just that division, the same division for converting from decimal to other number systems. So 7 converted to binary to be 1, 1, 1. 1 converted to binary, it will be 1. But it has to be 3 groups, so I'll put placeholders there. You can't put placeholders here after the 1 because it will distort your number. Because if you have a number like this one, it's not the same as 0, 0, 1. So I'll put the numbers in front here, not after the number. So this is what I needed to mention. So I've converted this number. So this is my number in binary. So let me just write it down. So it will be 1. If I want, I can even have these 2. Then the next set is this one, 1, 1, 1. The next set is 1, 1, 0. And the last set is 0, 1, 1 in base 2. So this is how we convert. I hope it makes sense. All right. So this is how we convert numbers. I think the next part will be just an example, another example, which is the same thing. Unfortunately, the example is for octa, for hexadecimal numbers. So I think in the slide I didn't include an example on octa, but luckily we've looked at an example. Now, so that's about the conversion from binary. So this number is actually in base 16, so it shouldn't have been here. The next part, converting, or here is the example, converting from octa to binary. So we're saying for each of these, create a 3-digit binary number. So 3 converted to binary like this, 7 converted to binary, 4 converted to binary. Then you put them together and you have your number in binary. Now, converting to base 16. If you have a number in base 16, hexadecimal, and you want to convert to binary, what you do, you are going to create, or you're going to convert each digit, each of these digits, convert it into a 4-digit binary number. Why 4-digit? Hexadecimal, the highest number in hexadecimal uses 4 digits. So for each of them, you put them in 4 binary into a 4-digit number. So we have this example, 2BA3. This number, we are saying you are going to convert each number into a 4-digit binary number. So it will be like this. You have 2, convert it to binary. It will be 1, 0. So to complete it, you put 2 zeros there. Then B, that is 11. 11 converted to binary is like this. A is 10 converted to binary is like that. 3 converted to binary is like that. Then you put them together. So that's how we convert numbers. Now, the two last things that I want to make mention of. The first one is number representation in computer systems. Now, in computer systems, you'll find that depending on the number system that you have, when representing data, you can have, for example, the most common one is 16-bit representation. Now, when we have a number, let's say, for example, let's say we have a number like this one, 1101. So this is a single number. So 1101, 1001. Okay. So they say this number is in base 2. So you have this number in base 2, and you want to show how it will be stored in a computer system. So the architecture that we have, so I say 1, 2, 3. Let me just draw this so that I can show, I can explain the point clearly. Don't mind the sizes. Ideally, if I was drawing nicely, all these will be the same size. So if we have 16-bit representation, you have 16-bit representation of a number, which you want to show how it will be stored in memory. So what I'm talking about now is data representation inside the computer. So if you have a system like this one, the first cell here is for the sign. Now, what this sign indicates, we have some numbers which are positive, other numbers are negative. So if a number is positive, the way we have, to indicate that it's a positive number, we put a 0. So for positive number, we'll put a 0. To show that the number is negative, we put a 1. Why they chose like this, I can't give an answer, but that's what we do. Now, so the first cell here indicates the number. Then this number that we have to represent, we're going to fill it in here. Now, the way we'll fill it in, we'll start from here, going to this side. So in a 16-bit representation like this one, the first bit indicates the sign, then the number will follow. So this position will start from here. So that is the first value here. The next one is 0 here. The next one is 0 here. The next one, that one. Then followed by a 1. Then the next one. Then the next one. Then the next one. Okay, so this is the representation of your number. Now, for these other cells that are there, they can't go empty. So we are going to fill them in with placeholders. Now, a placeholder would be the 0. So we are going to put zeros here. Don't mind, I have a better handwriting, but to write on a computer using the mouse is not easy. So please bear with me, where my handwriting is looking like that of a grade 1. All right. So what I've put from here to here, this is just to complete the bits, because I can't leave them empty. So the actual number itself ends here. Then whatever cells that remain here, we have to pad them. We have to put zeros there just to fill in the 16 bits. Then the first one here indicates the sign. If our number was a negative, so negative that, the sign here would have been, the value here would have been a 1. So this is about data representation. Now, the next part that I'll talk about is, let me just share this, then, okay. The systems that we use in computing, for example, the keyboard, the most common arrangement for a keyboard is the ASCII model. Now, this ASCII stands for American Standard Code for Information Interchange. It represents the way that characters will be. Now, when we have data which we want to represent in a computer system. For example, when I'm typing a message, hello John, how are you? Let me just write it. So let's say I have a message to say hello. Now this number, when it is being entered into a computer, there's one model, the ASCII model, that is used. So for each of these, they have been given integer values. For each of these characters, they have been given integer values, and it is those values that will be stored in that 16-bit we are talking about. So if a letter is a capital letter, for example, the letter H, its binary number is 72. And when you convert 72 to hexadecimal, it will be 48. If you convert to octal, it will be 110. So that is for the H. Then E, it has 69. Its number is 69. And then if you convert this 69 to hexadecimal, it will be 45. If it's in octal, it will be 105, sorry. So then the L, it's 76, just like that. Now the idea, what I want you to see, for example, capital letter A is at 65. The next letter, B, is at 66. C is at 67. D, 68. E, 69. 70, 71, just like that until you get to Z. Then small letters, they start from 97. 97, 98, 99, 100, just like that. So when you're entering a message, for example, hello, when that message is being transmitted from your keyboard to the processor, it is that number which is sent. So for example, the H is 72. So 72 is the one that will be sent. E is 60 something, 69. It's the one that will be converted. There are other forms that we can use for representing these number systems, but the most common one is this one. So this is what we can say about data representation. I hope it makes sense. Now, just a quick advice on this one. With number systems, for most people, we are kind of used to using our calculators to convert from one number system to the other. But for the sake or to ensure that you've understood, we would demand that you do not use a calculator. We would demand that you do not use your calculator and that you should show your working. So please get used. It's not very complicated. It's something that you can easily do without using a calculator. So please start doing that for the purpose of understanding what we're doing here. So this is where we end in this video. We'll see you in the next video, which will look at software. Thank you very much for watching. We end here.